13.1, sample space. So we talked about sample space the last time, and we noted that sample space is just the set of all possible outcomes of some action or some event, right? Yes?
I'm sorry, I didn't get a packet.
Okay, they're up here. So it's a set of all possible outcomes. So we're asking, what are some of the examples of situations we know where we know all possible outcomes? So in the case of a coin toss, for instance, we know that we can have heads or tails. So there are two possible outcomes. With the roll of a die, for instance, we have 6 possible outcomes, right? 1, 2, 3, 4, 5, and 6. I can roll a 1 or a 2 or 3 or 4 or 5 or 6 on any one roll of the die. Okay, letter grade. I don't want to write all this out, but there's A through F, and you can have pluses and minuses and all that stuff. So there are a set of all possible outcomes of a coin toss, of a roll of a die, of a letter grade. There are other things, like in baseball, if you're up to bat, there's a set of all possible outcomes for that, though it's pretty large. Right. So an event then is just an outcome or a set of outcomes or just multiple outcomes. So if we talk about an outcome of a sample space, we're talking about tossing the heads on a coin toss, or rolling a 3 on a roll of a die, or getting a B, or something like that. That would be an outcome, or a set of outcomes. I roll a die once and I roll a 3, I roll a die a second time and I roll a 4, that would be a set of outcomes. Or I roll 2 die at once and I roll a 2 and a 3, or whatever. That would be a set of outcomes, be multiple outcomes, which would be a part of this total sample space. So when I roll 2 die, for instance, we saw last time with that kind of square grid that the total number of outcomes for rolling a die, for the sum of the 2 numbers that you would roll with 2 die at once, is there are 36 possible outcomes. But an event would be getting a certain sum, or an event would be getting a certain set of sums or multiple sums after rolling multiple times, let's say. So make sure you know that distinction. It'll be important to know, especially when it comes to questions.
Do you have any of these people?
Okay, let's see.
Because it's it on the board. Go to C4 or S8.
Okay, let's see. Gavin, is that, I can't read the first name, but Medina, last name Medina, Tyrone, Anthony. Any of those guys here? Are they all juniors?
Gavin who?
What? Gavin Castaneda?
Oh yeah.
Okay. So it doesn't sound like they're here at all.
Okay. All right.
Thanks. Okay, so an event is an outcome or a set of outcomes in a particular sample space. Great. So if we flip a coin 3 times, what are the possible outcomes? This tree diagram is trying to show us what all the possible outcomes are. So think of this right here, these two, as my kind of first toss. The first time I flip the coin. On that flip, I could get either heads or tails. Now let's say I actually get a heads. So I'll circle that in green. So I land a heads the first time. That means that my second time is here. This is my second time tossing it. Again, I have 2 possible options, right? Heads or tails. Let's say I land a heads. Thanks. And then I can toss it a third time. And let's say I get tails or something. So that's one possible way. But these are all the possible outcomes that you could have when flipping a coin 3 times. But you should think of it chronologically, right? So you should think of it in terms of, okay, this is my first toss. I kind of then trace a certain path depending on the tosses. So I might go tails, tails, heads, or tails, heads, tails, or heads, tails, heads, or heads, 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 or something like that. So that's one way of representing all the possible outcomes. So then the question is, what is the sample space for the event flipping a coin 3 times and observing the number of heads? So we're going to be asking, okay, what's the sample space? So what are all the possible outcomes for the events or the action of flipping a coin 3 times and observing how many heads we get? I would ignore, if you're asked something like this, I would ignore observing the number of heads. because they're not asking you right now for the probability of flipping a heads 3 times or the probability of flipping a heads 2 times. They're asking you for what are all the possible outcomes for flipping a coin 3 times. So then all it's a matter of doing is counting. So I'm going to flip a coin 3 times, and I'm going to look at all the possible outcomes. So I flip a coin once. I have 2 possible outcomes, heads or tails. So the first time is 2. The second time then, I'm going to land on one of these. I don't know which, but I'll land on one of these. So then the second time, depending on which one I land, I'll still have 2 outcomes for the second toss. And on the third toss, I'll also have 2 possible outcomes, heads or tails. So 2. So ultimately, when I have it with what is the sample space, what are all the possible outcomes for flipping a coin 3 times, it's just 6. Now, if I want to know the probability for flipping heads 3 times out of 3 times, let's say, then I would need to do, okay, my first time I flip it, I have a half probability. Second time I flip it, I have a half probability. Third time I flip it, I have a half probability. So then I'd add that up. Well, it wouldn't be like that, sorry, but it'd be multiplied. But that's a separate question from sample space. So sample space is just what are all the possible outcomes, asking specifically for the probability of flipping a heads on some coin flip, let's say, is a completely different matter. So that would be, 1.2 times 1.2 is 1.2, so it'd be 1 over 8 would be my probability. So make sure that you are, people sometimes get confused about this kind of question. So about being asked, what's the probability of some event happening, so flipping the heads, as opposed to what are all of the possible outcomes when I flip a coin and try to get a heads. So in the first case, that's just 1, because I'm looking to see, okay, what's the probability of my getting 1 out of 2 options? My total amount of options is just 2. So if I roll two regular 6-sided dice, there are how many different outcomes? They give you the answer here of 36. And you can see they give you kind of part of how you would map this out. So we did it with ordered pairs here. So the first number in the parentheses is just your first time rolling a dice, or just one of let's just say it's the first dice that you roll. Let's say you every time you roll it, you land a 1. So for 6 times you land a 1, and then for each of those, it's possible to get with the second dice a 1, 2, 3, 4, 5, or 6. So you can think of it, well, for each number on the first sided die, for the 1, there are 6 possible combinations. 1, there's 6 possible combinations. For 2, there are 6 possible combinations. For 3, there are 6 possible combinations. Those aren't fractions, sorry, just assigning 6 to these numbers. So anyway, so it ends up being 36 for 2-sided die. Also, a way you can think about it is in terms of multiplication. So we'll get to this in the next lesson in 13.4. But one way to figure out the total set of outcomes for 2 events that are independent, so rolling 2 die at the same time, those are rolling 1 die and then the second die, those are 2 independent events because they don't affect each other. There are 6 options for the first one, 6 possible outcomes, and there are 6 possible outcomes for the second. You can just multiply those together and get 36. S4. I don't think so, no. Okay, sounds good. Will do. Bye. Okay. So now we have the question: if we roll if you roll 2 regular 6-sided dice and record the sum, what are your possible values? So what are your possible sums when you roll 2 6-sided dice? And here the answer is just the numbers 2 through 12. We don't include 1 because obviously, I can't roll a 1 and a 0 because the dice don't have 0 on them. So that's impossible. So getting 1 is impossible, but 2 through 12 would be all the possible outcomes for the sum of 2 regular 6-sided dice being thrown. Pretty intuitive. Right, so next we're just going to go over Venn diagrams, just kind of how do we read them, how do we fill them in. It's nothing, I hope I don't make it more complex than it needs to be, because it's not that complex, but sometimes it can be a little strange. And I think the examples that they included here on the notes are kind of strange when we get to the back. So here we have, oh my goodness, S4, yeah. Is Edward Vargas here? No. No, he's not here either. Okay, sounds good. Okay. Okay, so they're asking how many males and females are in the room. I'm not going to count this up, but let's say 12 males, 13 females, let's say. Right, so that's one way to represent this. And we represent it separate because there's really no overlap there. That's controversial. But anyway, there's really no overlap there between the set of males and the set of females in the room. But there is overlap here between how many students had A's in math, let's say, in English last year. I'm not going to ask about that either. But you might say, okay, like 10 had A's in math, 11 in English, and 4 had both, or something like that.
Yeah, if we did that, then that would mean that, I'm sorry, I can't read it right now. It's a 10.
Well, we're just coming up with arbitrary numbers right now.
With that, with the Venn diagram, that means 14 got an A in math, and 15 got an A in math.
Right, yeah, so you have to,
Minus the numbers.
right, yeah. So with Venn diagrams, you have to be careful with the overlap because depending on how they word the question, it's not always clear whether or not this both is included already in these numbers or not. So sometimes it's included separately. So like Ms. Fleming pointed out, sometimes it'll say, well, you have 10 who exclusively got A's in math but didn't get A's in English. And then you have 4 who got both, so it would be 14 in total for math. And then it would be 15 in total for English.
So does that make sense if they said if you got this kind of picture and they said how many kids got an A in English, you would have to add the 11 as 4? Because there were 4 who got A's in both, and then 11 who only got an A in English, 10 who only got an A in math. Does that make sense?
Right? So, okay, some nodding heads, some people looking skeptical. Does that make sense?
Yeah.
Okay. Right, so what we'll see on the back, I think, yeah, it's kind of interesting how they do this. Anyway, so going to the back, we have some examples. So, this one says 25 students are on the swim team, 14 of the swimmers play water polo, and 5 only play water polo. Okay, so then the questions are how many water polo players are there, and how many students participate in an aquatics program. Right, so one of the things to pay attention to first is the language used in the question. So it says here that 5 only play water polo. The word only is a good indicator that you're going to have 5 in this exclusive category, right? So 5 who only play water polo, they're not counted in the overlap. They don't swim at all. It's just they only play water polo. Okay, now 14 of the swimmers play water polo. So there are 14 in the both category because they're swimmers, they're on the swim team, but they're also playing water polo. So always remember that even if it's not labeled, this overlap here is the both, so where it kind of makes this football shape, sort of. It's both. Okay, and there are 25 students on the swim team. I'm taking the water polo players to not count as on the swim team, so I'm saying that 25 students are on the swim team. Okay, 14 are in this both category, so they're playing, they're swimming and they're playing water polo. But now we have to figure out how many people are just swimming that don't play water polo and swim. So if there are 25 students on the swim team, 14 do both, what's left over? Right, 11. It's just 25 minus 14. So we'd have 11 over here on the swim team. Okay, so does that make sense? Usually on these Venn diagrams, you're going to be using addition or subtraction to take the given information and then figure out kind of how many people are in one of these categories. So the given information here is that we have 5 who only play water polo, so 5 who are in this category who only play water polo. And then we have 14 swimmers, so they're on the swim team, but they also play polo, so they're in the middle because they overlap. And then that means we have to figure out how many are over here. In which case we say, well, there's 25 students in total who swim, 14 of them who also do water polo, so that means there has to be 11 to make up the difference who just swim. So how many water polo players? Well, we'd have 19 because we have 5 who only play water polo and 14 swimmers who also play water polo. So 19 in total who are playing water polo. And how many students are in the aquatics program? Well, we just add up 11 and 14, which would make 25. Another 5, that's 30. So 30 in total. Does that make sense how I got that? Okay. So a lot of times with Venn diagrams, it's just a matter of, it's not really a matter of using any formulas or calculating anything that's really hard. It's just a matter of reasoning through what they're saying and making sure you're paying attention to the language. Okay, so here's one. 40 students served detention yesterday. 25 worked on math, 18 worked on English, and 11 worked on both. How many worked on neither? All right, so we have 25 who worked on math. We have 18 working on English and 11 working on both. Now you might think this is odd, right? Because we have 25 working on math, 18 working on English. That's already over 40 students. That seems like it doesn't make any sense. And especially if we add in the 11 who worked on both, then we're way over 40. So how does that make sense? Well, the idea here is that, in this prior case, you could have said, well, okay, how many people swim? We do 11 plus 14, and that gives us the total, 25. Or how many swim and play polo, or how many play water polo? You just do the overlap plus this. Here, though, this isn't the case because all of these together don't equal the total number of students, the 40 students. So this means that these 11 people in the middle are already counted in the 25 and the 18. So there's some overlap of 11, but let's say there would be 7 over here and 4 over here or something. It means that we don't really actually know how many of the students only worked on math or only worked on English. That isn't clear in the question. But we do know that 11 worked on both. Okay, so then the question is, how do we figure out who worked on neither? Well, we have to figure out, because all of these add up to more than 40, we can't figure out, the number of people who worked on neither is just going to be a matter of subtracting some number from 40 to figure out the difference between how many worked on something and how many didn't. But we have to figure out, okay, how many students actually were there here, because this adds up way over 40. So we do that by subtracting the difference from the sum of both of these. So we're going to add up 25 and 18 and subtract 11 from that. That'll give us 43 minus 11, which is just 32. Okay, does everybody get the issue that we're running into here with these numbers?
Yeah.
How did you fill it out?
I did it with the 11 in the middle, which left 14, 17.
Okay, yeah, that's another way to do it. So another way to do it is to subtract the 11 from both sides already. So then you would have 14 here, 11 here, and 7 here.
So I have 35 students represented in my diagram, and then I had 8 left over in the corner.
Right, yeah. So both of these methods arrive at the same answer. So here you would then subtract 40 minus 32 because there are 32 students working on something, and then you get 8 left over. And here you would just add up, okay, I have a total of 14, 11, and 7. Sorry, let me move that up. I have 32 students here working on something, so 40 minus 32 equals 18. So there are 2 ways to do this. One is to just plug in the numbers as they give them to you, and then subtract the difference from both, or to just do that step implicitly and then fill in the diagram with the numbers, with 11 already subtracted from both quantities. But does that make sense why we have to subtract 11 from 25 and 18? Do people get that? Okay, because that's important. It's important when you recognize, okay, there's something wrong with these numbers here because the total is way over the number of students that they've told. They said there's 40 students, But if we add up all these numbers together, we're going to get 54 students, and that's a little over. So we have to figure out what's going on. Usually that just means subtracting the overlap from both of these quantities on the side. Okay, so there's an overview of Venn diagrams. Now we're going to do two-way tables. So this first one's just a matter of filling stuff in. So in a sample of 40 students, 15 males went on a summer vacation and 10 stayed in town, excuse me. Of the females, 9 went on summer vacation and 6 stayed in town. So we just fill it in. We look, okay, here's male, vacation, 15 males went on vacation. Then we look at, okay, home, male, 10 stayed in town or at home. And then we say, okay, females, 9 went on summer vacation, so female vacation, 9. And 6 stayed in town, so female home, 6. Okay, then we just make totals. So we want to know, okay, what's the total of all the males? So 15 plus 10, that's just 25. How many females are there? 9 plus 6, 15. Okay, how many went on vacation? So we're looking down this row now, vacation. 15 plus 9, which is 24. And how many went home? 10 plus 6, 16. And in total, you can either add it up the bottom, left to right, or the total, the top down, just 40. So that would be how you fill in one of these two-way tables. You just look for the intersection of different categories. So the intersection of vacation and male, how many males went on vacation, the intersection of female and home, how many stayed home, and then the totals for male, just going across, female, or number of on vacation, number who stayed home. Okay, now here's one where we have an incomplete table and we need to fill it all in. So anybody ever played like Sudoku or anything? You know about Sudoku? Yeah. So in Sudoku, you're given some numbers in some boxes, and you're trying to fill in boxes such that the numbers work out and come up to the same total, and you have 1 through 9 all in the same squares. Anyway, all sorts of stuff. This is similar, so you're just looking for basically ways to deduce what's in these boxes. Okay, so we're given a grand total of freshmen and sophomores as 100. Freshmen 28 yes, sophomores 14 no, and sophomores yes and no. So there are a total of 55 sophomores. So this is a good place to start because we have 2 sets of data, right? So we're looking at this one first, and we're going to say, okay, so there's some number of yes and some number of no, some sum that makes 55. So we're going to add some number plus 14 to be 55. Just a matter of subtracting 14. So then you get 41. So 41 goes here. Because we know that from left to right on this row, the sophomore row, 41 plus 14, and we get 55. Okay, that opens up the yes column. So now we have 2 values in the yes column, 28 and 41, and we're missing the total. So all we have to do is just add up 28 and 41 and get 69. Okay, and basically you're looking for rows in which you have 2 values, because that'll allow you to either subtract some number from a total to get what the other number should be to make that sum, or allow you to just add up 2 numbers that are supposed to be a total. So now you can see, okay, in the total row now I have 2 numbers. I'm missing one of the components here. So I can go 100 minus 69, have 31. Okay, now I just need to figure out what number adds to 14 to make 31. So I can just do 31 minus 14. This will be 17. And then just add across, or I could subtract 55 from 100, either one. I add 28 into 17, and I get 45. So again, just a matter of reasoning through the table, looking for rows where you have 2 values such that you can subtract a value from a sum, or from a total to get one of the other values, or we can just add up 2 values to figure out what one of the totals is. It's just a matter of making sure you're careful and reasoning through each step, making sure that you have the right components for each step.